if you ever get the chance to stand on the floor of a modern manufacturing plant, you absolutely have to do it.
Oh, yeah. It's an experience.
It really is. You look up and there's usually this massive, towering robotic arm. Maybe it is in a car factory, hoisting an entire engine block into the air like it weighs absolutely nothing.
Right. Or a colossal piece of earth-moving equipment at a quarry.
Exactly. And when we see those things, our brains just instantly default to this very primitive assessment. We look at the heavy steel, the massive bolts, the sheer physical footprint of the thing, and we just think, wow, that right there is power. That is brute strength.
Well, it is entirely visceral. I mean, your biology is reacting to an imposing physical presence that just looks completely unstoppable.
Right. But then you zoom in and you realize something almost eerie about how the world actually works.
Yeah.
If you were to walk up to that terrifying multi-million-dollar steel giant and you were to cut just 2 or 3 tiny hair-thin wires, yeah, or if you just removed a little piece of plastic the size of a coin from its elbow joint, that unstoppable titan is instantly paralyzed. It becomes nothing more than a very heavy, very expensive piece of abstract art. The whole illusion of brute strength completely shatters.
Which is fascinating, because it means we are living in a reality where the biggest, strongest, most intimidating machines on Earth are entirely at the mercy of the smallest, most invisible components.
Exactly. And that boundary is exactly what we are tearing apart today. We are looking past the heavy steel and doing a deep dive into the hidden command layer of human civilization.
The command layer, I love that term.
Right. We are looking at these fascinating engineering and philosophical notes titled Actuation, Sensing, and Interface Components. The mission here today is to demystify exactly how machines actually receive a command, how they physically sense the world around them, and how they transform from a passive object into an obedient, active agent.
And what I find so compelling about this framework is that we aren't just looking at dry textbook engineering specs.
No, not at all.
We are looking at these highly technical, invisible components through a really unique metaphorical lens from the sources. We are framing this entire ecosystem of parts as a persona, a character named Liz.
Yes. Liz, I absolutely love this concept.
It's brilliant.
It is. When you look at the philosophy of how machines operate, the author uses Liz as the embodiment of power as performance, desire as doctrine, and control as art form.
Right. She is not someone who runs around frantically chasing attention.
No, she is an apex performer who curates the room. She quietly enforces the emotional tone, and reality simply shifts to accommodate her.
Which is exactly what these parts do.
Exactly. At first glance, you might think, what on earth does an industrial valve or an electrical switch have to do with a hyper-competent commanding persona? But the deeper you get into the material, it makes perfect, terrifying sense.
Because these tiny components are entirely about perception, absolute command, and forcing the physical world to comply with an intention. And if we zoom out and look at the actual stakes here, without these Liz-like entities, these tiny uncelebrated sensors, actuators, switches, and servos, modern life doesn't just slow down. It instantly and catastrophically collapses.
Give me an example of that. What are we talking about?
Well, think about a proximity sensor. If that fails, an elevator doesn't know it reached the lobby, and it just drives itself straight into the concrete pit.
Oh, wow. Yeah.
Or if a pedal interface fails, a car driving at highway speeds loses its electronic throttle control and its anti-lock brakes. Entire city water grids rely on these tiny pressure transducers. Without them, massive underground mains would just burst and flood the streets.
So we're talking about the true mechanics of power here.
Yeah.
And who or what actually holds the leash on the machines you think you own?
The machines we think we own. Yeah, that is a heavy thought to sit with.
It really is. Okay, let's unpack this. Let's start at the absolute foundation, the anatomy of machine obedience. The core concept we need to tackle first is this idea of closing the gap.
Closing the gap?
Right. It's the gap between human intention, what I want to happen, and physical reality, what actually happens.
And that gap is incredibly vast. I mean, conceptually, an engine just spinning continuously on a test stand is simple. A pump moving fluid through a pipe is simple.
Right.
But a robotic arm, picking up a fragile microchip, accelerating to blinding speeds, stopping on a dime, and placing that chip onto a circuit board with a tolerance of 0.1 millimeters.
That is not simple at all.
No. That requires a relentless, high-speed conversation between intention and reality.
And to have that conversation, the notes lay out 4 specific existential questions that every single automated machine must answer. It's almost like a checklist for mechanical consciousness.
I like that.
And the very first question the machine asks is, what is happening right now?
Right. And the machine answers that question using sensors. Sensors act as the machine's eyes, its ears, and its skin.
Okay.
Before a machine can do anything intelligent, it has to measure the physical reality of the environment it exists in. Is it hot? Is it vibrating? How much light is in the room?
How much physical force is pressing against this lever?
Exactly. The sensor's entire job is to take that physical analog reality and translate it into an electrical signal, usually a voltage or a current, that the machine's digital brain can actually understand.
Because a computer chip doesn't know what hot is, it only knows that a wire is currently sending it 5 volts instead of 2.
Precisely.
So that brings us to question 2 on the existential checklist. What does the operator want? And this is our entry point, right?
Yes, this is the interface layer.
Yeah.
You have the reality of the world from the sensors, but now you need the human desire.
So switches, pedals, that sort of thing.
Exactly. Your industrial joysticks, your touch screens. This is the exact moment human intention is translated into a command protocol. It's your foot physically pressing the accelerator pedal to say, I desire to go faster.
Which brings us to question 3. And this is the one that really blows my mind. Where am I, and did I do it correctly?
Ah, yes. This is the difference between an intelligent machine and a dumb tool.
Hmm.
This question is answered by components like encoders and limit switches.
Okay, unpack that for me.
Well, in biology, we call this proprioception. If you close your eyes right now and I tell you to touch your left earlobe with your right index finger, you can do it instantly.
Right, without looking.
You don't need to look at your hand because your nervous system constantly tells your brain exactly where your limbs are in 3-dimensional space. Machines need that too.
Wow, okay.
They use rotary encoders to know exactly, down to the microdegree, where their mechanical limbs are positioned at any given millisecond.
That is incredible. And finally, question 4. How do I physically change the world?
Actuators. These are the muscle fibers, the solenoids, the servos, the heavy hydraulic cylinders.
So they actually do the pushing and pulling.
Exactly. The actuator is the final recipient of the conversation. It takes the human command, it takes the environmental data, it takes the energy, and it violently or delicately converts it into physical movement. It forces reality to change.
I really want to lean into this analogy of the human body because it makes this so tangible.
It really does.
If we imagine a machine as a body, a purely mechanical device, let's say a bicycle, is effectively just a skeleton.
Right.
It has bones, it has joints, it has the potential for mechanical advantage, but it has no nervous system.
Oh.
It is completely dead until you, the external force, manually push the pedals.
Exactly.
But the moment you start adding sensors, switches, and servos to a mechanical frame, suddenly it has nerves, it has reflexes, it can flinch, it can react to the world without you doing the physical work.
And that transition from a dead skeleton to a nervous system raises a profound engineering philosophy. It breaks the entire mechanical world down into 2 categories: open-loop systems versus closed-loop systems.
Okay, let's define those.
An open-loop machine is fundamentally blind. It receives a command, it blindly executes the action, and it completely stops. It never ever checks to see if the action actually worked. It just arrogantly assumes reality complied.
So it's like me putting on a blindfold, spinning around, and throwing a dart at a dartboard. I performed the action of throwing perfectly, the muscles fired, the dart left my hand, but I have absolutely zero idea if I hit the bullseye or if I hit the wall or if I just embedded the dart into someone's leg.
That is a flawless analogy, yes. And, in many basic applications, open loop is totally fine.
Like what?
A sprinkler system on a timer is open loop. It turns on at 5 a.m. for 20 minutes. It doesn't care if it's currently pouring rain out or if the lawn is already completely flooded. It just blindly executes the command.
Right. It doesn't sense the world. But a closed-loop system is different.
Completely different. It senses, it acts, it evaluates the result, and then it corrects itself.
A thermostat.
The perfect example. A thermostat measures the ambient room temperature. It realizes reality is at 65 degrees, but your intention is 72 degrees.
So it turns on the heats.
Right. It commands the furnace to turn on. But here is the critical part. It doesn't just turn it on and walk away. It keeps sensing. It watches the room change, 68, 70, 72.
And then it stops.
Only when reality exactly matches your desire does it shut the system off. It constantly corrects its own behavior based on feedback from the world.
And bringing this back to our persona, the whole Liz concept. In Lizian terms, operating in an open loop is simply embarrassing.
Oh, absolutely.
Yelling a command into the void and walking away without checking if anyone listened is not power, it's just noise. True power requires intense surveillance, it requires minute correction, impeccable timing, and consequence.
Yes.
Liz doesn't just walk into a room and shout a demand, she commands an action, she watches the entire room's body language shift, and she micro-adjusts her posture and her tone until the physical reality matches exactly what she wanted.
That is the essence of feedback control. It really is the absolute crown jewel of this entire technological category. Feedback control is the reason we can fly unstable fighter jets. It's the reason a surgical robot doesn't crush a human organ, and the reason our power grid doesn't collapse every time a factory turns on its machines.
Okay, so if these are the biological organs of a machine, let's look at the specific cast of characters that make up this anatomy. From the brute force muscles down to the high precision nerves. Let's start with the broad umbrella term for muscles, actuators.
Right. An actuator is, quite simply, any device that converts stored energy into physical action or motion.
Okay.
That energy can come in many forms. It could be electrical current, it could be pressurized hydraulic oil, or it could be compressed air. But they behave incredibly differently.
Right, and there are two basic camps of motion that everything falls into, linear and rotary.
Yeah.
Linear is pushing and pulling in a straight line. Rotary is spinning, turning, twisting.
Yeah.
Let's tackle the linear movers first, starting with what feels like the most ubiquitous one, the solenoid.
A solenoid is an electromagnetic actuator, and it is beautifully simple. It provides a very quick, snapping linear motion.
Snapping, like a quick pop.
Exactly. If you open one up, inside you will find a coil of copper wire wrapped around a hollow tube. Inside that tube is a movable plunger made of iron or steel. When you send electrical current through that coil, it generates an instant, concentrated magnetic field. That magnetic field forcefully sucks the iron plunger inward.
Oh, I see.
And the moment you cut the electricity, the magnetic field collapses, and a mechanical spring violently pushes the plunger back to its starting position.
I know exactly what this is. This is that incredibly satisfying click or clack sound you hear all over your house and car.
Oh yeah, everywhere.
Yeah.
Like when you hit your key fob and your car doors instantly lock that loud thud inside the door, that's a solenoid plunger slamming into place.
Exactly right.
Or when you push your glass against the ice maker in your fridge and you hear a sharp click right before the water dispenses. That's a tiny solenoid snapping a water valve open.
Yes, they are incredibly fast, they are easily controlled by simple electronics, and they are relatively cheap. But they have a major limitation. They are limited in force, and they are limited in stroke length. A solenoid can give you a fast, sharp push over a fraction of an inch, but it cannot move a boulder. Right. You aren't going to lift a car with a solenoid.
No. When you need real, uncompromising, earth-moving power, you leave electromagnets behind and you step up to fluid power, specifically hydraulic cylinders.
Hydraulics, the real heavy lifters. When I think hydraulics, I think of the shiny metal arm on a backhoe just ripping through concrete.
Yes. Hydraulic cylinders use pressurized liquid, which is almost always a specialized oil.
Okay, why liquid?
The underlying physics principle that makes hydraulics so terrifyingly strong is Pascal's law, which relies on the fact that liquids are fundamentally incompressible.
Meaning you can't swish them.
Right, you cannot squish oil into a smaller space. So if you have a hydraulic pump that pressurizes oil to, say, 3,000 pounds per square inch, and you force that oil into the back of a cylinder, it pushes against the internal piston.
And because it won't compress?
Because the oil absolutely refuses to compress, it transfers 100% of that force directly into moving the rod outward. It generates immense, stiff, slow, unyielding power.
Unyielding is the perfect word. I mean, if a hydraulic cylinder is pushing and your arm gets in the way, the cylinder doesn't care. It doesn't bounce, it just crushes.
Exactly. It's unforgiving. But what happens if you take that exact same metal cylinder, but instead of pumping thick, heavy oil into it, you pump air? Then you have pneumatic cylinders.
Pneumatics. This is air pressure. But wait, air does compress. If I take a bicycle pump and put my thumb over the nozzle, I can push the handle down halfway just by squishing the air inside. Doesn't that completely change how the machine behaves?
It changes everything because air compresses. Pneumatic motion is inherently different from hydraulic motion. It is springy. It is spongy.
Oh, okay.
If a pneumatic cylinder hits an obstruction, it will bounce and cushion against the compressed air. It does not have the extreme force density of a hydraulic system.
So it's weaker.
Yes, but what it lacks in brute crushing force, it makes up for in speed and cleanliness. Air flows incredibly fast.
And it's not messy.
Crucially, yes. If a pneumatic airline blows out on a factory floor, what happens? You just hear a loud hissing noise and harmless air blows around. But if a high-pressure hydraulic line blows out, you have a massive, slippery, highly flammable environmental hazard that shuts down production for hours.
Which is exactly why you see pneumatics on things that need to be fast, clean, and safe, like the doors opening on a city bus. When those rubber doors close on your arm, they don't snap your bones like a hydraulic ram would. They just bounce off you with a satisfying swoosh.
Right.
Or in food packaging plants, where you have machines punching cardboard boxes and sorting apples at lightning speeds. You obviously can't have toxic hydraulic oil leaking near food.
Precisely. Those are your linear movers. Brute force, speed, and snaps.
Yeah.
But then we have the rotary movers, and specifically what we call the smart movers, the servos.
Servos. Okay, let's really dig into this because this feels like where the magic of modern robotics actually lives. A servo isn't just a motor, because if I pull a little DC motor out of a toy car and hook it up to a battery, it just spins endlessly until the battery dies.
Right, that's an open loop.
But a servo is different.
Vastly different. A servo is a complete, self-contained ecosystem. It consists of 3 parts working in perfect harmony. It has a high-quality motor to provide the physical twisting force. But physically attached to the back of that motor is a highly precise sensor, usually an encoder, that reads exactly how far the shaft has turned.
And the third part.
Built into the housing is a digital controller, a tiny computer.
So it's a motor that actively watches itself.
Yes. Let's say the main computer tells the robotic arm's elbow joint, turn exactly 45.5 degrees. The servo's internal controller applies power to the motor. The motor starts spinning. Simultaneously, the encoder on the back is reading the rotation in real time, counting the microscopic degrees, 40, 42, 44. As it approaches 45.5, the controller automatically reduces the current to slow the motor down.
And if it goes too far?
If the heavy arm carries momentum and accidentally overshoots to 45.6 degrees, the encoder instantly detects the error, tells the controller, and the controller throws the motor into reverse for a microsecond to pull it back to exactly 45.5. It constantly measures its own error and erases it.
Wow. It is the ultimate closed-loop device. It has memory, it has self-awareness, and it has the ability to correct its own mistakes faster than the human eye can even process.
Exactly.
That's why they use them to aim the mirrors on lasers, or stabilize the camera gimbals on drones, or constantly adjust the steering flaps on an autonomous aircraft. It's not just about moving. It's about moving perfectly despite the chaos of the outside world.
That's spot on. So those are the muscles. But muscles are useless without senses. Let's differentiate the 3 main ways a machine feels the world: the limit switch, the generic sensor, and the encoder.
Okay, let's start with the limit switch. In the notes we're looking at, this feels like the absolute blue-collar worker of the sensing world.
That is the perfect description.
Yeah.
A limit switch is a cheap, rugged, purely mechanical device. It usually have a little metal lever with a roller on the end or a stiff plunger.
Where do they put it?
It is mounted at the extreme end of a machine's travel path. When a heavy, moving part of a machine physically slams into that lever, it pushes it down, which physically snaps a set of electrical contacts, open or close, inside the housing.
It's like a bouncer at a club. It stands at the edge of the machine's universe and says, you cannot go any further. The ride stops here.
Yes.
Think about your microwave oven at home. Have you ever noticed the little plastic hooks on the microwave door?
Oh, sure.
When you close the door, those hooks push deep into the frame and click a tiny mechanical limit switch. If that switch isn't physically depressed by the door, the microwave just absolutely refuses to turn on the magnetron and blast radiation into your kitchen. It is a physical failsafe.
Right. It relies entirely on physical contact. But then you have sensors broadly, which often detect conditions without physical contact.
Like proximity sensors.
Exactly. A proximity sensor can use an electromagnetic field to detect a piece of steel floating an inch away from it. A photoelectric sensor shoots a beam of light across a conveyor belt to count boxes without ever touching them. A pressure transducer measures the microscopic bending of a silicon crystal to tell you the water pressure in a pipe.
So they translate the physics of the world into continuous electrical data?
Yes. And finally, encoders, which we just touched on with the servos.
Right.
Encoders are the peak of precision position tracking. They take rotational movement and chop it up into countable digital data. Imagine a tiny glass disc attached to a spinning shaft.
Okay, a glass disc.
That disc has thousands of microscopic black lines painted on it. As the disc spins, an LED shines light through the glass, And a receiver on the other side counts every single time a black line breaks the light beam. That's an optical encoder. It can tell a computer exactly how many fractions of a degree a shaft is turned.
Okay, I have to stop you here and push back on this a little bit.
Right.
We just established that an encoder can track movement down to the microscopic fraction of a degree level using lasers and glass discs. Probably not.
No. In fact, if you put an optical glass disc inside a dusky, humid, vibrating garage, it would get covered in grime, the light beam would fail, and you'd be trapped outside.
That makes sense.
All the motor actually needs to know is, did the door hit the concrete floor? That's it. So you put a $2 heavy-duty mechanical limit switch at the bottom of the track. When the door hits the floor, it crushes the switch, the circuit breaks, and the motor cuts out.
And it doesn't care about the dust.
Exactly. A limit switch doesn't care about dust, it doesn't care about humidity, and it doesn't require a microprocessor to decode its signal. It just keeps doing its dumb, vital job for 20 years. A machine only ever needs to be as smart as the task demands. Any extra intelligence is just an invitation for failure.
Appropriate precision. That makes so much sense. So now that we understand what these organs and senses do conceptually, we really have to talk about what they are physically made of. Because as our persona Liz would say, the glamour and the sales pitch might be in the shiny exterior housing, but the actual enduring power is entirely in the metallurgy.
Yes. And this brings us crashing into the harsh, unavoidable realities of physics. Specifically, energy and friction.
The enemies of all machines.
We like to think of machines as clean and perfect, but no energy conversion is perfect. The universe demands attacks on every action. Whenever an actuator converts electricity or fluid pressure into motion, it loses energy. It bleeds energy as radiant heat, it loses it to microscopic fluid leaks, it loses it to sound and vibration, and most destructively of all, it loses it to friction.
Friction is the ultimate double-edged sword, isn't it? Because we absolutely need it for the world to work. Without friction, tires wouldn't grip the road, clutches wouldn't engage, and we couldn't even pick up a cup of coffee.
Exactly.
But the very thing that makes movement possible actively destroys the machine every single time it moves.
It is a relentless war of attrition. Friction provides necessary damping and grip, but it guarantees wear. The iron plunger scraping inside a solenoid tube, the heavy rubber seals dragging against the inside of a hydraulic cylinder, the pivoting steel pin holding a brake pedal, they're all engaged in a slow, losing battle against friction.
Just grinding themselves away.
Yes. Metal scrapes against metal, ripping microscopic chunks of material away in a process called galling. And this is exactly where material science becomes the hard dividing line between a component that runs flawlessly for a decade and a cheap knockoff that fails catastrophically in a week.
Okay, let's break down some of the materials on the front lines of this war. Let's start with king of industry. Steel and stainless steel.
Carbon steel is your absolute baseline for strength and rigidity. If you need a shaft that won't snap under immense torque or gear teeth that won't shear off, you use steel. But ordinary carbon steel has a fatal flaw.
It rusts.
It oxidizes. It rusts. And rust is catastrophic for an actuator. Imagine a heavy hydraulic cylinder on a bulldozer. It is a shiny steel rod that pushes in and out of the housing. If that rod rusts, the rust doesn't just sit there.
Right.
Rust is essentially iron oxide, which is abrasive. It acts exactly like microscopic sandpaper. When that rusted rod gets pulled back inside the cylinder, the rust particles instantly shred the delicate rubber seals holding the oil back. Suddenly, you have high-pressure hydraulic fluid spraying everywhere.
Oh, man. So how do you stop a steel rod from turning into sandpaper?
Two ways. First, you heat treat the steel, altering its internal carbon matrix to make it incredibly hard. Then you plate it. That's why the rods on construction equipment are so brilliantly shiny.
Right, they look like mirrors.
They're coated in hard chrome plating, which is incredibly smooth, resists rust, and allows the rubber seals to glide effortlessly over the surface.
But what about stainless steel? That doesn't rust, right? Why not just make everything out of stainless?
Because it's expensive, and it's notoriously difficult to machine. Stainless steel is brilliant because it is alloyed with chromium. When exposed to oxygen, that chromium instantly forms an invisible microscopic oxide layer that protects the underlying iron from rusting.
So it heals itself.
If you scratch stainless steel, the chromium instantly reacts with the air and heals the protective layer. But you only use it where you absolutely have to. You see stainless steel as a mandatory requirement in food processing plants, where every machine has to be blasted down nightly with caustic cleaning chemicals and hot water. or in marine environments where salt water destroys ordinary steel in days.
Okay, what about the non-ferrous metals, the lighter stuff? Aluminum, brass, and bronze.
Aluminum is the metal of speed and mass production. It's lightweight, it naturally resists corrosion, and it's incredibly easy to extrude into complex shapes.
So you see it a lot in factories.
If you look at an automated factory floor, almost every pneumatic cylinder body and sensor housing is made of anodized aluminum. Brass is soft and easily machined into airtight threaded fittings for air hoses, but bronze, well, bronze is where the engineering philosophy gets truly poetic.
Yes. I was so fascinated by this when I was looking at the notes. The concept of engineered martyrdom. Explain what bronze actually does inside a machine.
Bronze is an alloy of copper and tin, and in the world of heavy machinery, it is used as a sacrificial metal.
Sacrificial.
Let's say you have a massive, spinning, hardened steel shaft, and it needs to pass through a stationary cast iron housing. If the steel shaft rotates directly against the iron housing, the friction will generate immense heat, and eventually the two metals will gouge each other, gall and weld together.
Oh, wow.
You would destroy the entire multi-thousand-dollar shaft and the housing.
Which is an absolute nightmare.
An expensive nightmare. So instead of letting them touch, an engineer machines the hole in the iron housing a little bit larger and presses a soft bronze sleeve called a bushing into the gap. This steel shaft now spins inside the bronze sleeve. The bronze is intentionally softer than the steel. It is also slightly porous, meaning it can actually absorb and hold lubricating oil like a metallic sponge.
So the oil provides a microscopic fluid film between the steel and the bronze.
Exactly. And here's the genius part. Over millions of rotations, as friction inevitably takes its toll, the tough steel shaft remains absolutely flawless. It doesn't wear down at all.
Oh, because the bronze takes the hit.
Instead, the soft bronze slowly, willingly grinds itself away into dust. It sacrifices itself to protect the expensive components. When the machine gets loose, the mechanic just pulls out the heavily worn cheap bronze bushing, taps a new $3 bronze sleeve into place, and the machine is literally as good as new. The component is designed to die so the system can live.
That is brilliant. Okay, let's pivot to the electrical side. Copper. This is the lifeblood of anything electromagnetic, right? We're talking solenoids, relays, servos.
Absolutely.
Yeah.
None of those work without copper. Copper is highly conductive, allowing us to build the electromagnets that turn electrical current into physical motion.
Yeah.
Inside every servo motor and solenoid is a coil made of hundreds of wraps of copper wire.
Okay.
And this is exactly where cheap manufacturing cuts corners with disastrous results.
How so? Wire's just wire, right?
Not at all. High-quality actuators use pure, oxygen-free copper wire to minimize resistance, and every single strand of that wire is coated in a high-temperature, microscopic layer of insulating varnish.
Why varnish?
This ensures the electrical current travels through the entire length of the massive coil rather than jumping across the wires. But cheap, counterfeit parts, they might use undersized wire to save pennies. They might even try to use aluminum wire painted to look like copper, and they use cheap, low-temperature varnish.
So what happens when that cheap solenoid gets put to work on a busy factory floor?
It overheats. The undersized wire creates too much electrical resistance, which generates immense heat. That heat melts the cheap varnish. Suddenly, the bare copper wires touch each other inside the coil, creating a short circuit. The electrical current bypasses the coil, the magnetic field collapses, the machine stops moving, and the internal heat spikes so fast that the component literally burns up from the inside.
Releasing that acrid white magic smoke every technician dreads.
Yes, the magic smoke. Once that's out, it's dead.
And what about the soft stuff? The polymers and elastomers, the rubbers and plastics. We don't really think of rubber as a structural machine part, but it's holding all the fluids in.
Without elastomeric seals, modern fluid power doesn't exist. These are your O-rings, your wiper seals, your flexible dust boots. And the chemistry of rubber is mind-bendingly specific. You cannot just use any rubber for any job.
Because they react chemically to the fluids they touch, right? Give me an example of a mismatch.
Let's say you have a basic nitrile rubber O-ring. Nitrile is great for standard mineral-based hydraulic oils at room temperature. But let's say a maintenance worker grabs that nitrile O-ring and installs it in an aerospace actuator that uses specialized fire-resistant phosphate ester hydraulic fluid running at 200 degrees.
What happens?
The chemistry goes to war. The molecular lattice of the nitrile rubber physically absorbs the synthetic chemicals. The rubber begins to dramatically swell up, expanding to twice its size. It gets soft, gummy, and then under high pressure, it simply extrudes and blows out of the metal joint.
Wow.
A perfect $2 million titanium aircraft hydraulic system is completely disabled in a matter of minutes because a technician used a 50-cent seal made of the wrong polymer chain. You have to specify exact elastomers like FKM Viton or EPDM, depending entirely on the fluid chemistry and the thermal load.
So we have all these amazing materials, steel, bronze, copper, high-tech polymers. How do they actually get formed into these complex parts? The notes we're reviewing go deep into manufacturing realities, and it completely shifted how I look at metal parts.
Yes, the journey from raw earth to finished component is brutal. You generally have four main pathways. The first is casting. This is where you melt iron or aluminum until it's liquid and pour it into a sand or ceramic mold.
Sounds pretty standard.
It is incredibly cost-effective for making complex, bulky shapes, like the heavy iron body of a massive water valve. But casting has a dark side. As the liquid metal cools, it can trap tiny gas bubbles, creating internal porosity. The metal isn't uniformly dense. It can be brittle.
Which means you can't use a cast part for something that takes a violent shock, right? Because a hidden bubble inside the metal acts as a stress riser, and the whole part can crack in half.
Exactly. So when lives are on the line, you don't pour liquid metal. You use forging. Forging is taking a piece of solid, glowing red-hot steel and literally smashing it into shape between massive hydraulic dies under thousands of tons of pressure.
I remember learning about this. Forging actually alters the crystalline grain structure of the metal, right? Like aligning the grain in wood to make it stronger.
That's a perfect analogy.
Yeah.
The immense pressure aligns the grain flow of the metal to follow the shape of the part. That makes forged parts phenomenally strong and highly ductile, meaning they will bend before they ever snap.
So they don't shatter.
Exactly.
Mm.
This is why critical components, the brake pedal arm in your car, the heavy rod ends on a crane's hydraulic cylinder, the hooks used for lifting, are always forged. You absolutely do not want a brake pedal snapping in half under your foot because of a microscopic cast iron defect.
And yeah, machining.
Machining is subtraction. You take a solid block of metal and use computer-controlled spinning blades, lathes, and mills to cut away the material you don't want. This is how you achieve absolute microscopic precision.
Right.
The internal spool of a high-end hydraulic valve has to be machined to tolerances of 10,000ths of an inch so it can hold back high-pressure oil without using rubber seals.
That's incredible.
And finally, you have injection molding. Heating plastic pellets and shooting them into steel molds under pressure. This is what gives us the billions of cheap, lightweight housings for sensors, electrical connectors, and switches.
Now, what about 3D printing? Because additive manufacturing feels like the darling of the modern tech world right now. People act like we're just going to 3D print jet engine actuators on demand in the future. But from what I'm reading, there are massive caveats.
Huge caveats. Additive manufacturing is miraculous for prototyping. You can design a part on a computer and hold it in your hand 4 hours later. It is also incredible for creating complex internal geometries that a traditional drill bit could never reach, like intricate cooling channels inside a manifold.
Sure.
But for high-stress, safety-critical control components, it struggles immensely.
Why? If you're using 3D printed titanium, isn't it just as strong as a block of solid titanium?
No, and that is a really common misconception. When you 3D print a metal part, you are essentially welding microscopic layers of metal powder on top of each other, one by one. The bond between the layers in the vertical z-axis is almost always slightly weaker than the horizontal strength.
Oh, I see.
It creates anisotropic strength, meaning it's strong in one direction, but vulnerable to shearing forces in another. It also struggles with microscopic internal porosity.
So it's just really hard to trust.
It's incredibly hard to certify. If you are an aerospace engineer and you need to sign your name to a document saying a flight control servo will survive 10,000 hours of vibration and thermal shock, well, you know exactly how a solid block of forged aluminum behaves. But a 3D printed part might have a microscopic fusion defect hiding between layer 400 and 401. Until non-destructive scanning technology becomes perfect and cheap, 3D printing will struggle to replace forged or machined parts in life-or-death actuators.
Okay. Looking at all this material science, the metallurgy, the polymers, the forging, it brings me to a realization that I find incredibly profound.
What's that?
When a massive piece of infrastructure fails, let's say an automated shipping crane drops a container, or a factory assembly line grinds to a halt, it rarely happens because a giant solid steel beam just snapped in half. It almost always fails because a $3 rubber seal swelled up and leaked hydraulic fluid.
Yep.
Or a 10-cent plastic gear inside a servo stripped its tiny teeth. Or a mechanical limit switch got a single speck of grease on its copper contact and stopped sending a signal. The weakest link that brings down the empire is always a tiny, invisible interface part.
It is the living embodiment of the horseshoe nail proverb. For want of a nail, the shoe was lost. The horse was lost. The rider was lost. The battle was
Well,
lost.
exactly.
In modern industrial terms, for want of a clean sensor, the servo was blinded. Because the servo was blinded, the robotic arm crashed. Because the arm crashed, the packaging line stopped. And because the line stopped, the factory bled $100,000 an hour in lost revenue. A multi-million-dollar facility brought to its knees by a speck of dust on a $30 component.
Here's where the plot really gets interesting. It's not just the physical materials or the dust that can trick you. Let's say you have a part that is made of absolutely flawless titanium, perfectly machined and tested. It will still violently destroy your machine if it's the wrong specification. As our persona Liz would say, looking similar is not the same as being equal, darling.
And this is arguably the most dangerous trap in the world of maintenance and engineering, the absolute danger of visual identity. We are biologically wired to believe that if two things look exactly the same, they are the same. But in the world of sensors and actuators, visual identity is a liar. Two parts can be physically identical down to the millimeter, but be fundamentally dangerously incompatible.
Give me a tangible example of that. How bad can it actually be to swap identical-looking parts?
Imagine holding two industrial pressure sensors in your hands. They both have the exact same brushed stainless steel cylindrical body. They both have the exact same half-inch threaded fitting on the bottom. They both have a 4-pin electrical connector on top. You could screw either one of them perfectly into the water pipe on your machine.
Okay, so they look identical.
But internally, their digital languages are completely different.
How so?
One sensor is designed to output an analog voltage signal. It sends between 0 and 10 volts back to the computer depending on how much pressure is in the pipe. The other sensor outputs a current signal. It sends between 4 and 20 milliamps of electrical current.
Wait, pause right there. Why 4 to 20 milliamps? Why not 0 to 20? If the pressure is 0, shouldn't the signal be 0?
That is a brilliant question, and explaining why reveals the paranoia of industrial engineering. Think about it. If your sensor outputs 0 milliamps when the pressure is 0, and the computer receives a 0 signal, how does the computer know if the pipe is actually empty, or if a rat just chewed through the sensor wire?
Oh, wow. It wouldn't know. It would read 0 either way.
Exactly. A 0 signal is ambiguous. But if the sensor is calibrated to output 4 milliamps when the pressure is absolute 0, the computer knows the sensor is alive and listening. If the computer ever sees 0 milliamps, it instantly sounds an alarm. Broken wire, system fault. It's an automatic self-diagnostic built into the physics of the current.
That is incredibly smart. Okay, so back to our two identical-looking sensors. One is 0 to 10 volts, the other is 4 to 20 milliamps. What happens if I grab the wrong one?
Let's say your machine's computer is programmed to read the voltage sensor. You accidentally install the current sensor. It fits the pipe perfectly. You plug the wire in. But when the system pressurizes, the sensor is sending milliamps of current into a computer terminal that is expecting volts.
Oh, no.
The controller is utterly blind to that language. The pipe could be moments away from bursting under maximum pressure, and the computer will sit there thinking the pipe is completely empty, happily commanding the pumps to run harder and faster until the steel violently ruptures.
All because the physical housing lied about the internal language. And the notes mentioned this happens with pneumatic cylinders too, right? With hidden magnets?
Yes. You can buy 2 air cylinders. Same physical length, same mounting holes, same shiny aluminum tube. But one model has a tiny invisible magnetic ring integrated into the internal piston, and the other model doesn't.
Why does it need a magnet inside?
Because factories use magnetic proximity sensors clamped to the outside of the aluminum tube to detect when the cylinder has fully extended. The aluminum doesn't block the magnetic field, so the external sensor sees the internal magnet pass by and tells the computer, action complete.
So if you use the wrong one?
If you install the non-magnetic cylinder by mistake, the air pushes the rod out, the machine moves physically, but the external sensors never trigger. The computer sits there, staring at a silent sensor, assumes the cylinder is physically jammed, and throws an emergency fault code, shutting down the entire assembly line. And the poor technician is left staring at a cylinder that physically worked but digitally failed.
This is exactly why deconstructing the numbers stamped on the side of a part is so critical. There is a whole language of specifications. We hear terms like model numbers, part numbers, and serial numbers. For the layman, they all just look like a barcode. What is the actual difference?
It's a hierarchy of specificity. A model number identifies the general family and the broad physical configuration of the component. The text gives a great real-world example, an SMC brand pneumatic cylinder with the model number CDQ2B3250DMZ.
Okay, that just sounds like a password. What does that actually tell an engineer?
Every single letter and number is a strict code. To a trained engineer, that string spells out the exact geometric profile. It's a compact series cylinder. It has exactly a 32 mm internal bore size. It has exactly a 50 mm stroke length. It has a built-in magnetic piston, and it has specific metric mounting threads on both ends. You can look at that number and know exactly how big the chunk of metal will be.
So that's the model number. What about a part number?
A part number is much more specific. It defines the exact, purchasable, highly calibrated assembly, usually intended for a specific larger machine. Take an automotive component, like a Ford accelerator pedal assembly, part number 9L8Z9F836A. That number doesn't just describe a pedal. It represents the exact physical plastic bracket molded for a specific dashboard layout, the specific mechanical return spring tension that Ford wanted for driver feel, and the exact mathematically calibrated dual voltage curves of the sensors inside it, specifically approved by the EPA and the safety boards for a certain vehicle platform.
You can't just slap a generic pedal in there. And finally, serial or batch numbers. Those are the fingerprints.
Yes, serial numbers are for absolute traceability. Let's say a rubber factory mixes a batch of O-rings incorrectly on a Tuesday in September, and those bad O-rings get installed into 500 hydraulic valves. 3 months later, they start failing in the field.
So they use the batch numbers to track them down.
Exactly. The batch numbers allow the manufacturer to track down exactly which serial numbers of valves receives the bad rubber, issue a targeted recall, and pull only those specific units off the shelf globally, rather than recalling a million perfectly good valves.
Let's decode one more. This is an even more complex specification code from the source materials. Imagine you pull an optical encoder out of a shattered robotic arm, and the label says ENC 1024 PPR5V ABZ 6mm. Walk me through the anatomy of that code.
It reads like a book once you know the language. ENC simply tells you the component type. It's an incremental encoder. 1/4 PPR is the critical performance metric. It outputs exactly 1,024 digital electrical pulses for every single 360-degree revolution of its internal shaft.
Okay.
5V dictates the electrical supply. If you feed it 24 volts instead of 5, you instantly fry the internal microchip. ABZ tells the computer what kind of signal pattern to expect. It sends an A signal, a slightly offset B signal to determine which direction the shaft is spinning, and a Z index pulse that fires once per revolution to establish a home position. And 6mm is the mechanical interface. The physical metal shaft sticking out is exactly 6 millimeters in diameter, meaning a 1/4-inch coupling won't clamp onto it tightly enough.
I look at a code like that and I have to ask, does this really matter? If I'm a mechanic working a late shift and a machine is down, and I find a replacement encoder on the shelf that fits the 6mm shaft, but the label says 1,000 PPR instead of 1024 PPR, is 24 pulses really going to break the universe? Why not just use the whole 1,000 and get the factory running?
What's fascinating here is the compounding, cascading consequence of that exact tiny math error. Let's trace it out. You put a 1,000 pulse per revolution encoder into a robotic arm, but the robotic arm's central computer is hard-coded to believe it takes 1,024 pulses to make one complete circle.
Okay, I'm following.
The computer commands the arm to turn exactly 360 degrees. The arm starts spinning. The replacement encoder counts out 1,000 pulses and stops sending data because it completed its circle. But the computer says, wait, I've only received 1,000 pulses. I need 24 more to finish the circle. So it keeps the motor running, pushing the arm further until it receives 24 more pulses from the start of the next rotation.
Oh no, so it overshoots.
Exactly. It physically overshoots its target by a few degrees. But here is the nightmare. It doesn't know it overshot. It thinks it is in the perfect position. So the next time it moves, it overshoots again and again. Every single time the arm moves, that tiny angular error multiplies and accumulates in the digital dark.
Wow.
But the robot progressively drifts out of physical alignment while remaining perfectly confident in its own digital reality. And within 20 minutes of high-speed operation, that arm will violently smash a heavy payload directly into a concrete pillar or a human worker because the digital map and the physical territory have completely decoupled.
The machine acts on the lie it is fed? That is chilling. And there's another example of a lie here involving safety switches, the normally open versus normally closed contacts.
This is a classic trap. Electrical switches come in two flavors. Normally open means the circuit is physically broken and electricity cannot flow until you press the switch to connect the wires, like a doorbell. Normally closed means electricity is always flowing through the switch, and when you press it, it physically breaks the circuit to stop the flow.
So why does that matter? For safety.
Let's say you have an emergency stop button or a safety limit switch on a dangerous factory door. Industry standard dictates these must be normally closed. The machine requires a constant, uninterrupted flow of electricity through that switch just to stay alive. If you open the door, the switch is pressed, the circuit breaks, power stops, and the machine halts.
That makes sense.
But why not use a normally open switch, where opening the door sends a signal to stop the machine? Because of the reality of the physical world. What if a rat chews through the wire leading to the door switch? Or a forklift accidentally snags and cuts the cable?
Ah, if the wire is cut, the switch can't send the stop signal when the door opens.
Exactly. If you use a normally open switch and the wire is cut, the safety system is silently dead. A worker opens the door, steps into the machine, and the blades keep spinning because the stop signal never reached the computer. But if you use a normally closed switch, the system is fail-safe. If a forklift cuts the wire, the constant flow of electricity is broken.
So the machine stops anyway.
The computer instantly detects the loss of signal, assumes the door was opened, and shuts down the machine safely. If you swap those two identical-looking switches, you are actively dismantling a life-saving system.
When you lay it out like that, it becomes incredibly obvious why strict specification is a matter of life and death. But eventually, despite perfect specifications and flawless materials, friction wins. Every single component inevitably degrades and fails. And when that happens, we leave the clean world of engineering design and we enter the messy, expensive world of maintenance. This is where the economic and legal battles truly begin.
Maintenance is not a physical task. It is a profound philosophy of deduction. It requires a specific kind of intellectual rigor. The source material emphasizes this brilliantly by laying out the chain of diagnosis. A weak technician sees a machine stop, looks at a failed actuator, and just mindlessly swaps the part. A master technician doesn't do that. They follow the invisible chain of causality. Command, to power, to signal, to motion, to feedback.
Trace that chain for me. Show me what a master technician sees that the novice misses.
Let's imagine a massive manufacturing line, and suddenly a heavy pneumatic air valve stops opening. The conveyor belt grinds to a halt. The novice technician looks at the valve, says the valve is broken, and spends 2 hours unbolting it and installing a brand new $500 valve. They turn the machine on, and nothing happens. The new valve doesn't move either.
Because they treated the symptom, not the disease.
Exactly. The master technician approaches the exact same stop machine, but starts at the beginning of the chain. Command. Did the main computer actually tell the valve to open? Yes, the digital log shows the command was sent. Move to power. Does the solenoid on top of the valve have enough magnetic strength to shift the internal spool? The master puts a screwdriver near the coil, feels a weak magnetic pull, and realizes the solenoid is struggling.
Well, why is it struggling?
That's the question. It shouldn't be. The technician pulls out a multimeter and checks the signal. The solenoid is rated for 24 volts of direct current, but the meter only shows 14 volts. The voltage is bleeding out somewhere.
So they have to trace the wire backward.
Yes. They trace the electrical cable 30 feet back through the oily belly of the machine, and they find a plastic junction box. They open it, and it is dripping with water from a roof leak. A 50-cent copper connector block inside is heavily corroded, covered in green oxidation. That corrosion is acting as a resistor, choking off the electrical voltage before it ever reaches the valve.
So the multi-thousand-dollar failure had absolutely nothing to do with the heavy pneumatic valve itself. It was entirely caused by a drop of water on a piece of copper 30 feet away. If you don't follow the chain of diagnosis, you're literally just throwing extremely expensive parts at a ghost.
That is the difference between working blind and having mechanical awareness. As our persona Liz would do, she would never attack the loud, obvious symptom first. She would calmly observe the room, find the hidden leverage point, and systematically make the whole system confess its true weakness.
Make the system confess. I love that. But once you actually extract that confession and find the broken part, you have to make an economic choice. Do you invest the time to repair the broken component, or do you just throw it in the trash and replace it? Where's that line drawn?
The line between repair and replace comes down to a calculus of economics, internal complexity, and safety. You generally repair large, expensive, accessible parts. Let's go back to our bulldozer. If a massive, 4-foot-long hydraulic steering cylinder starts leaking fluid, you do not throw away a $3,000 piece of forged steel. A technician unbolts it, brings it to a clean bench, carefully disassembles it, hones the steel rod to remove scratches, and replaces the $20 worth of internal rubber seals and bronze bushings. You rebuild it, test it, and put it back to work.
So you repair things where the metal value is high.
Yes, you also repair extremely large multi-kilowatt industrial servo motors by pressing in new ceramic bearings.
Because the raw material cost far outweighs the labor cost. But on the flip side, what components dictate that you just blindly throw them away and replace them?
You replace components that are cheap, permanently sealed, or highly safety critical.
Hmm.
Let's look at the cheap and sealed parts. If that little mechanical limit switch on your microwave door stops clicking, you do not pull out tweezers, pry apart the ultrasonically welded plastic housing, and try to delicately bend the tiny copper contacts back into shape.
Hmm.
Even if you could, the labor time isn't worth it. You throw the $2 switch in the trash and snap a new one in.
And what about the safety critical side?
That is where the automotive pedal sensor comes in. Those are sealed, ultrasonically welded, permanently calibrated units. If the dual potentiometers inside your car's accelerator pedals start giving erratic voltage readings to the engine computer, you absolutely do not try to open the plastic housing and resolder the microcomponents. If you make a mistake and the pedal shorts out while driving, the car could go into uncontrollable acceleration. The liability is astronomical. You discard the entire assembly and bolt in a factory-new certified pedal.
And this transition right here, the mandate to replace entire proprietary assemblies rather than fixing small internal parts, this brings us to a massive, boiling, socioeconomic battle in modern technology, the right to repair.
Yes.
When I was reviewing the notes for this deep dive, it highlighted this as a true civilizational shift. It points out that for all of human history, a tool belonged entirely to whoever held it. If you lived in ancient Rome and your wooden lever broke, you went to the forest, cut down a branch, whittled a new lever, and got back to work. You didn't owe the lever maker a subscription fee.
The autonomy of the user was absolute.
Yes. But today, a farmer in the Midwest might spend $600,000 to own a state-of-the-art combine harvester. And yet, if a single $30 emissions pressure sensor on the exhaust pipe fails, that farmer is completely digitally locked out from fixing their own machine.
Because of software coupling. The manufacturers fundamentally change the nature of the physical part. They take that physical sensor and they embed a microscopic cryptographic chip inside it. They pair that specific sensor's digital signature with the tractor's main engine control computer using encrypted firmware.
Which means even if the farmer has the mechanical skill to unbolt the broken sensor, and even if they drive to the parts store and buy the exact, genuine, brand new replacement sensor, when they plug it in, the tractor refuses to acknowledge it.
Exactly. The physical connection is perfect, but the digital handshake fails. The tractor's computer says, I see a sensor, but it does not have the cryptographic key I expect. Therefore, I will not allow the engine to start. The only way to make the tractor run again is to call an authorized corporate dealer, wait 3 days for a technician to drive out to the farm, and pay them hundreds of dollars just to plug a proprietary laptop into the dashboard and click a software button to authorize the new sensor.
I am going to passionately argue for the farmer here. This is the ultimate ownership paradox, and it feels fundamentally unjust. You bought the machine, you paid the bank for the steel, but you do not own the ecosystem that keeps it alive. This is exactly why entities like the Federal Trade Commission in the U.S., enforcing the Magnuson-Moss Warranty Act, and the European Union with its new eco-design directives, are fiercely stepping in.
Yeah.
They are fighting against what they see as unlawful monopolistic repair restrictions, demanding that independent shops and everyday owners have the legal right to access parts, diagnostic codes, and software tools. It's about not being held hostage by the company that sold you the product.
I completely understand the visceral anger of the farmer. But to be perfectly impartial, as we are required to be when analyzing these civilizational shifts, we must recognize that the original equipment manufacturer, the OEM, has a very valid, incredibly serious side to this debate. The argument for maintaining strict cryptographic lockdown is fundamentally about physical safety, cybersecurity, emissions compliance, and exact calibration.
Okay, I'm listening. Make the case for the OEM. Why should a manufacturer be allowed to lock down a machine I own?
Let's escalate the stakes away from a tractor and look at a robotic surgical suite, or the fly-by-wire servos on a commercial airliner, or even just the anti-lock braking sensors on a modern electric vehicle. These are life-critical closed-loop systems. If the system is fully open to the right to repair, what stops an untrained corner-cutting mechanic from replacing a highly sensitive brake pressure transducer with a cheap, uncalibrated knockoff part they bought online?
I see where this is going.
If that knockoff part sends a voltage curve that is off by just 5%. The car's computer might miscalculate the friction of an icy road, pulse the brakes incorrectly, and send a family into a ditch. By cryptographically locking the system, the OEM is guaranteeing that only heavily vetted, certified parts, installed by technicians trained in exact calibration procedures, are allowed to touch life-critical systems. Furthermore, in an age of cyber warfare, an open digital port on a tractor or a city water pump is an invitation for hackers to inject malicious code into the machine's nervous system. The OEM lock is a digital firewall against catastrophic physical liability.
Okay, that is a sobering and terrifying argument, safety and liability. But let's swing back, because while safety is paramount, it is also the perfect, unassailable shield for corporate greed. Make the countercase for the independent aftermarket and the right to repair.
The counterargument points out that manufacturers aggressively weaponize safety to create lucrative, captive monopolies on repair parts and service hours. When that rural farmer's tractor goes down during a narrow harvest window, waiting 3 days for an authorized tech isn't just an inconvenience. It threatens their entire crop yield and livelihood. Independent repair shops, high-quality aftermarket parts, and open documentation are absolutely essential for keeping rural economies functioning, keeping small factories running without paying exorbitant service contracts, and keeping legacy machines alive after the original manufacturers stop supporting them.
Right.
When repair is monopolized by the OEM, it artificially inflates prices, and worst of all, it guarantees that perfectly good machines are prematurely abandoned and thrown into landfills just because corporate won't authorize a software patch.
And sitting right in the murky middle of this intense debate between the OEM and the legitimate aftermarket, there is a third, genuinely dark category that ruins it for everyone: counterfeits.
Yes, we have to clearly separate aftermarket parts from counterfeits. A legitimate aftermarket part is an honest third-party component built by a different company to meet or exceed standard industry specifications. It has its own brand name on the box. A counterfeit part, however, is a malicious lie. It is a dangerously cheap, low-quality sensor or switch dressed up with forged logos, fake part numbers, and fraudulently applied UL safety certification marks.
How do you even counterfeit a limit switch? It's just plastic and metal.
It's terrifyingly easy. A counterfeiter takes the internal copper mechanism of a switch rated for 2 amps of current, shoves it into an identical plastic housing, pours black epoxy over it so you can't see the tiny wires, and laser etches a fake rating of 20 amps onto the side, complete with a forged safety laboratory stamp. As the text puts it so beautifully, a fake safety switch is not a bargain. It is a liability wearing a costume.
Because if a factory manager buys that fake switch online thinking they got a great deal and runs 15 amps of current through it,
The undersized copper instantly melts. It doesn't break the circuit. It literally catches fire. And if it catches fire inside a dust-filled grain silo or an oil refinery, a $20 fake switch causes a catastrophic explosion. If counterfeit parts enter the supply chain, all the philosophical debate about the right to repair instantly goes out the window, because the very foundation of mechanical trust is broken.
this tension between cheap, disposable parts, locked proprietary ecosystems, and the constant cycle of replacement doesn't just frustrate mechanics and farmers. It has created a literal, physical mountain of a problem that affects everyone on Earth. It leads us directly into the environmental and civilizational footprint of these tiny components.
We are talking about the footprint of the invisible billions.
Right. When we think of pollution, we think of tailpipes and smokestacks. But there are billions and billions of these actuation and sensing parts embedded in the background of our world. Your washing machine at home has a dozen solenoids and lid switches. Your car has hundreds of actuators and sensors buried in the chassis. A single automated Amazon warehouse has millions of them running the conveyor belts. And every single one of those microscopic components carries a heavy environmental debt from the very moment the raw ore is ripped from the earth.
Let's trace that debt, starting with the critical minerals involved. If you look at the International Energy Agency's 2025 outlook, the geopolitical reality is stark. These tiny command components are incredibly hungry for highly specific, difficult-to-extract materials. Copper, obviously, is required by the ton for all the electromagnetic coils. But the real bottleneck is rare earth elements, specifically elements like neodymium.
Neodymium. I hear that word constantly in tech. Why is it so important?
Because of the physics of magnetism. Neodymium, when alloyed with iron and boron, creates the Nd-Fe crystal structure, which produces the strongest permanent magnets commercially available. If you want to build a servo motor that is incredibly small, lightweight, and capable of generating immense rotational torque, which you need for an electric vehicle drive system, or a wind turbine, or a compact robotic joint, you absolutely must use neodymium magnets. You cannot achieve that power-to-weight ratio with standard iron magnets.
But the problem isn't just finding the metal in the ground, it's the refining process.
Exactly. The Earth has plenty of rare earth elements, but they are mixed with hundreds of other minerals and radioactive isotopes. The chemical processing required to separate and refine pure neodymium is toxic, highly energy-intensive, and environmentally devastating. And currently, the global refining capacity is incredibly concentrated. A vast majority of the world's processing happens in just a few nations.
Which creates a bottleneck.
A massive one. This makes the entire global supply chain for automation, the green energy transition, and even national defense systems incredibly fragile. If a geopolitical conflict disrupts the export flow of rare earth magnets, you simply cannot build the high-performance servos required to manufacture electric cars or steer fighter jets. The hidden hierarchy extends to global trade.
And that is just the beginning of the component's life. What happens at the end of its life? This brings us to the e-waste crisis. The statistics here are staggering. The UN Global E-Waste Monitor reported that in 2022, the world generated 62 million metric tons of electronic waste.
62 million tons. To visualize that, it would fill a line of heavy transport trucks wrapping entirely around the equator of the Earth. And the most damning part of that statistic is this. Only about 22% of that massive volume was properly formally collected and recycled. The other 78% was either dumped in landfills, illegally exported, or improperly incinerated, releasing toxic heavy metals into the atmosphere and groundwater.
And a massive intentional driver of this crisis is the manufacturing concept of planned obsolescence and disposable design. This goes back to our discussion about the right to repair, but on a structural level.
Is where the ruthless economics of assembly clash violently with environmental stewardship. In modern manufacturing, labor time is the most expensive variable. So engineers are pushed to design components that can be assembled in seconds. Often, it is mathematically cheaper for a manufacturer to take a plastic housing containing a complex circuit board, a pressure sensor, and a mechanical switch, and instead of screwing the housing together with 3 metal screws, they use a process called ultrasonic welding.
Which is what, exactly?
It uses high-frequency acoustic vibrations applied to the plastic pieces while they are held together under pressure. The vibration creates instant, localized heat that melts the plastic, fusing the two halves into a single, permanent, seamless block. It takes a fraction of a second on an assembly line. No screws to buy, no threads to strip, no quality assurance checks to see if the screw is tight. It's cheap and it's fast.
But the environmental cost at the end of the line is devastating, because ultrasonic welding completely destroys the possibility of repair.
Exactly. Let's say 10 years later, the tiny 10-cent mechanical limit switch inside that welded housing inevitably wears out from friction. The repair technician arrives, but they cannot open the housing to simply swap the 10-cent switch. If they try to pry it open, the welded plastic shatters, destroying the entire unit. They are forced to throw away the entire $300 smart assembly.
That assembly contains pure copper windings, rare earth neodymium magnets, silicon microchips, and toxic flame-retardant plastics.
But almost all of it will end up in a landfill, because separating permanently welded mixed materials is a labor-intensive nightmare. It takes too much time for a recycler to smash the plastic off, pry out the magnet, and unscrew the copper. It's not economically profitable to recycle, so the raw materials are lost forever.
I want you, the listener, to think about what this actually means in your daily life. It is an engineered dependency. It's like buying a brand new luxury car, and a year later, the leather on the steering wheel gets a little dirty. But instead of letting you clean it or replace the cover, the manufacturer has permanently welded the steering cover to the steering column, and the column has a cryptographic chip tied to the engine. So because the leather got dirty, you have to throw the entire 2-ton car into the garbage crusher and buy a new one. It prioritizes quarterly corporate parts revenue and assembly line speed over the long-term sustainability of the planet.
Which is exactly why the ideal path forward, the push being made by environmental engineers and policy frameworks like the EU's eco-design directives, involves in completely rethinking how we build things. It relies on 3 main pillars: modularity, remanufacturing, and design for disassembly.
Break those 3 pillars down for me. How do they actually fix the problem?
Modularity is ending the era of the smart monolithic block. It means building systems in discrete, easily swappable blocks. If the sensor fails, the housing should allow you to unplug just the sensor and click a new one in without replacing the heavy actuator arm or the motor it's attached to. You isolate the failure.
And remanufacturing, that sounds like recycling, but it's different, right?
It is vastly superior to recycling. Recycling is taking a heavy steel hydraulic cylinder, melting it down in a massive energy-intensive furnace, and casting a new block of steel. Remanufacturing is taking that worn-out cylinder, fully disassembling it, running the steel through a precision hone to remove the microscopic scratches, replacing only the soft rubber seals and putting it back into the market with a brand new warranty.
So it's much greener.
You save the immense, raw, embodied energy that it took to originally mine, cast, and forge that steel block. And vitally, remanufacturing requires human intelligence. It creates highly skilled, local mechanical jobs, rather than just feeding a smelter.
And finally, design for disassembly.
This is a mandate on the original engineers. It means you stop using ultrasonic welding and permanent adhesives. You intentionally design the product with standardized screws, metal clips, and snap fits. You design it so that at the end of its 20-year life, an entry-level worker at a recycling plant can take a power drill and completely separate the pure copper, the rare earth magnets, the aluminum, and the plastic into clean, easily recyclable streams in under 60 seconds. You design for the death of the product from day one.
To truly understand how we arrived at this hyper-complex present, where a microscopic silicon chip can dictate whether a 20-ton tractor is allowed to harvest corn, and where global supply chains hang on the processing of neodymium, we have to zoom all the way out. We have to look at the deep history of how humanity actually learned to make the physical world obey us.
It is an incredible historical and philosophical arc. We're talking about the long journey from pure human muscle to mechanical levers to digital algorithms.
Let's travel back to the ancient era. What was our interface with the world then? Because we didn't have solenoids, we didn't have electricity.
Our interface was purely mechanical, and it was entirely about amplifying physical force. The foundational technology was the lever. It's one of the classic simple machines. If you, a human with limited muscle mass, could not move a 2-ton stone block with your bare hands, you didn't give up. You negotiated with gravity and physics.
Right, you got a lever.
You slid a long, rigid piece of timber under the stone, placed a fulcrum near the mass, and applied downward force at the far end. The lever acted as an analog multiplier, trading distance for force. You were still providing the energy, but the tool amplified your command.
And we also had early rudimentary control systems that didn't require humans to constantly watch them, right? The notes mention Roman plumbing.
Yes, the Romans used brilliant floating valves to regulate water levels in their aqueducts and holding tanks. It was incredibly simple but effective. As water filled a tank, a hollow wooden or hollow copper float would physically rise with the water level. That float was attached to a mechanical linkage that slowly closed the inlet pipe.
Like a float in a modern toilet tank.
Exactly. When the water reached the desired height, the float pushed the valve completely shut. As water was consumed, the float dropped, opening the valve again. That is a rudimentary sensor, the float and actuator. The valve, working perfectly together in a closed feedback loop without any human intervention.
It's a mechanical thermostat for water. But things stayed relatively quiet for centuries. Fast forward to the late 1700s, the dawn of the Industrial Revolution. Things get much, much bigger. We tap into chemical energy.
By tapping into chemical energy, the world became vastly more dangerous. We learned to burn coal to boil water to create high-pressure steam, driving massive iron engines that powered entire textile factories. But early steam engines had a terrifying fatal flaw. The amount of steam entering the engine was controlled by a man manually turning a heavy iron valve.
Which is an open-loop system.
Exactly. And the danger of an open-loop steam engine is catastrophic. Imagine a factory floor with 50 looms connected to a central steam engine by belts. The engine is chugging along perfectly, but suddenly the shift ends, and 40 of those looms are disconnected. The physical load on the engine instantly drops. But the massive steam valve is still wide open, pouring high-pressure energy into the machine.
Without the heavy load holding it back, the engine is going to speed up.
It doesn't just speed up, it runs away. The engine spins faster and faster and faster until the extreme centrifugal force literally tears the cast iron flywheel apart, sending massive chunks of shrapnel flying through the brick walls of the factory, killing workers and destroying the facility. A human operator could not react fast enough to constantly adjust the valve every time a load changed. The machines were too powerful for human reflexes to control.
Enter James Watt in 1769. This is one of the greatest engineering leaps in human history.
Absolutely. James Watt observed this chaos and invented the centrifugal flyball governor. This was a massive civilizational breakthrough in control theory. The governor consisted of a vertical spindle driven by the rotation of the steam engine itself. Attached to the top of the spindle were two hinged arms, and on the end of each arm was a heavy brass or iron sphere, the flyballs.
So as the engine spins, the spindle spins.
Yes, and as the engine spins faster, the spindle spins faster. The physics of centrifugal force, the same force that pushes you into your car door when you take a sharp turn, causes those heavy metal balls to swing outward and upward against the pull of gravity. But here's the stroke of pure genius. Those swinging arms were physically linked to the main steam valve.
Oh, wow. So as the balls swing up,
The physical upward arc of the balls pushes a lever down, which slowly chokes off the steam pipe. So if the engine suddenly loses its load and tries to speed up, the balls fly outward, the linkage pulls the valve shut, choking off the energy, and the engine is forced to slow down. When it slows down, gravity pulls the balls back down, which smoothly opens the valve again, letting more steam in.
it is entirely mechanical, physical calculus. It is an absolutely perfect closed-loop feedback system. It senses its own rotational speed, compares it to the physics of gravity, and physically actuates the valve to correct the error in real time forever. The machine regulates its own heartbeat. It is the dawn of civilization-scale feedback control.
From there, we hit the electromagnetic era in the 19th century. Once we understood electricity, we realized we didn't have to rely entirely on clunky mechanical linkages and spinning balls. We invented the solenoid, which we discussed, and the electrical relay. This fundamentally changed the geography of control. Now, a person could push a small button in a control room, and a low-voltage electrical signal could travel a mile down a copper wire, energize a massive solenoid, and instantly open a heavy floodgate or ring a warning bell. Human command was finally liberated from the constraint of physical distance.
And then the 20th century arrives. World War II and the Cold War push this entire field into absolute hyperdrive.
War always forces technological leaps because war forces machines to respond to threats vastly faster than human reflexes can process. This era accelerated the development of radar, sophisticated hydraulic servos, and the complex mathematics of control theory. Think about an anti-aircraft gun on a battleship. A human being looking through crosshairs cannot calculate the speed of an incoming dive bomber, the pitch of the ship in the waves, and the wind speed fast enough to turn the heavy metal cranks and hit the target.
It's mathematically impossible for a human brain.
So we built analog computers and heavy-duty servos. The radar dish automatically tracks the target, feeding continuous electrical position data to the servos, which violently swing the multi-ton gun turret to track the plane perfectly, correcting its own aim 10 times a second. We also needed flight surfaces that could automatically stabilize early jet aircraft that were fundamentally aerodynamically unstable.
And that intense life-or-death wartime technology eventually bleeds into the civilian digital era. In the 70s and 80s, we get CNC machines, computer numerical control. Suddenly, servos and digital computers are bolted to lathes and mills, allowing a spinning cutting tool to carve a block of steel with robotic, microscopic precision, following a digital blueprint perfectly, over and over, all day long.
And today, we are stepping into the era of AI and predictive maintenance. Control is no longer just about moving. It is about predicting the future. Today, the components are networked via the industrial Internet of Things. A modern high-end servo motor running a packaging line doesn't just hold its position and report its speed. It constantly monitors its own internal temperature. It uses tiny accelerometers to measure the microscopic acoustic vibrations inside its own ceramic bearings.
It listens to its own bones.
Yes. And it feeds that vibration data into an onboard AI model. If the bearing starts vibrating at a frequency that matches the early acoustic signature of microscopic galling, the servo doesn't wait to break. It sends an automatic digital message over the factory network to the facility manager's phone saying, "My internal bearing is showing signs of degradation. Based on my load history, I will likely fail in exactly 3 weeks. Please automatically order a replacement part and schedule maintenance for the upcoming weekend shift."
It is predicting its own death to save the machine. That is wild.
The philosophical takeaway here, which the source text dwells on so beautifully, is the overarching concept of mediated agency. These components, from the Roman float valve to the James Watt governor to the AI servo, they all symbolize humanity's relentless need to turn our invisible intention into real-world, physical consequence. We no longer negotiate directly with nature using our bare hands and brute strength. We use leverage, fluid pressure, electromagnetism, and digital logic to cooperate with physical laws. We have created layer upon layer of mediation between our desire and the outcome.
You know, applying this engineering concept of feedback loops to personal human psychology is a fascinating exercise. The notes mention the concept of open loop living, and when you apply that to a person, you know exactly who they are talking about. Open-loop living is acting blindly without checking the result. It's the manager who barks orders but never checks if the team actually understands them. It's the person who talks constantly without listening to the room, making major life decisions without looking at the fallout, repeating the exact same interpersonal mistakes over and over because they have disabled their sensory feedback. They are throwing darts blindfolded.
And the opposite of that, closed-loop living, is the very definition of emotional maturity. It follows the exact same logical sequence as a high-end servo mechanism. You set a conscious intention. You perform an action in the world. That's your actuator. But you don't stop there. You intensely observe the outcome of your action on the people around you. That's your sensor. You compare the reality of the room to your original goal. That's the internal controller. And then, crucially, you put your ego aside and you correct your behavior. You adjust your trajectory to close the gap.
If we bring this all the way back to the bigger picture and back to the Liz persona we started with, the text makes a profound observation. It notes that exerting control without ethics or awareness is simply domination. It's tyranny. But constantly responding to the world without any internal control or boundary is just chaos. You are just a leaf blown by the wind. The true art form, the apex performance of living, is command paired with continuous, hyper-aware feedback.
Exactly. True power isn't just having the brute energy to push something out of the way. Power is knowing precisely where to apply the leverage, knowing exactly when to stop, knowing how to read the microscopic feedback from the room, and having the internal discipline to make the system move exactly when you decide it should, and not a moment before.
All right, as we bring this massive deep dive to a close, let's look at the most underrated and important takeaways from exploring this hidden command layer. For me, it's realizing the absolute primacy of the sensor. The actuator is the muscle, yes, but the sensor is what gave human civilization mechanical awareness. Before sensors, our machines were deaf, blind, and dangerous, and the limit switch. I just have a profound new appreciation for the humble $2 mechanical limit switch. It's the rugged bouncer at the edge of chaos, just clicking away in the dust, taking the hits, and keeping the physical universe from tearing itself apart.
For me, the ultimate theme here is the paradox of modern ownership. The source materials make this incredibly clear. Availability is power. If you can access the command layer, you hold the power. But the modern paradox we all face is that the physical boundary of ownership has blurred. You may hold the legal title to the machine, the expensive electric car, the massive farm tractor, the smart refrigerator in your kitchen, but you do not actually own or control the digital, cryptographic, and supply chain ecosystem that allows it to function. You own the steel, but the corporation owns the nervous system.
Which leads me to a final thought for you to take with you today. Think back to where we started. We looked at a massive, incredibly powerful robotic arm rendered completely paralyzed and useless by the removal of one tiny invisible component. As our civilization accelerates, we are actively filling every single physical object around us, from our kitchen appliances to our vehicles to the heavy infrastructure of our cities and eventually to our own medical implants, with proprietary sensors, locked firmware, and cloud-connected actuators.
The world is becoming entirely mediated.
It is, and the provocative question we have to sit with is this. What happens to human freedom and human agency when the physical objects you bought and paid for and rely on for your very survival simply refuse to obey your physical commands without first pinging a server and receiving digital permission from a corporate entity hundreds of miles away? When the machine answers to the cloud before it answers to you, who is actually in control?
It is a profound structural shift in what it actually means to possess something in the 21st century.
It truly is. It changes everything. Thank you so much for joining us on this deep dive into the hidden machinery, the silent components, and the invisible logic that runs our world. We'll see you next time.